did that work? Sure did. All right, it is number 6. And again, I added the copper and I added some links because I'm going to build on this problem. Is that 10K on the left? Yeah, I think it is. Yeah, 10K. I just didn't write it very well. Yep. All right, so to get stress, we have to know loads. So our stress equation is P over A, and that's load over area. So I'm going to kind of elaborate on stress a little bit. This is actually called average stress. It's the stress that is across the cross-sectional area, okay? This cross-section is round. This cross-section is square. So what you want to think about in these kind of problems, when you're trying to get the average stress or the stress that this whole thing feels in general, you have to know the load that travels through that member, right? So if it's a truss, we got to find the load in the members. If it's some kind of a frame, then we got to find the load in the member. That was all statics, right? So this one's given us the loads. We just have to think about what the internal fibers are feeling. So the way I do it is I kind of cut it in my head, or I draw a new picture. If it's complicated, I'll just draw a new picture. But what I do is I say, okay, I'm going to think about those fibers right down the middle of this. I'm going to cut it, and I need to know what those fibers are feeling, right? So if I look to this side, 10 comes through, 10, I know it's in equilibrium. Everything's in equilibrium through the class, okay? Which means it's not moving anywhere. All the forces have to equate to 0. So that means, well, if I got 10 coming in, there's got to be 10 going this way. And if I look at these two, that's true, right? The difference between those are 10. So what this section is feeling is 10 kips. Does that make sense? All right. And it's over this round section. So if I drew, I'm going to try, I'll just kind of make it elliptical. So here's my cut. That's this cut, right? And if I drew the stress diagram, it would be the same kind of a cylinder, right? With all these little, actually it's pointing in, this one's pointing in, so it's compressive, right? It would go all the way around and on all the areas. In other words, the stress is the same across that cross section. If you get further away from the ends, probably in this region here, all the stress is the same. At the very ends, we can get some stress concentrations depending on how the load is connected, but we don't know anything about that. And we're just doing average stress for now. Does that make sense? It's the stress over that area. All right, so we know it's P over A. So it's 10 kips divided by, I need the area of the 125. So I can use pi d squared over 4. Is that correct for the diameter one? I think that's correct for the diameter one. Or you can use pi r squared, right? Either one. So let's run that. And I'm just going to leave this as K. It's going to end up to be KSI, right? All right. And that, everyone knows K is 1,000. So let's see. I have my 10,000. All right, divide by, I'll put the pi in. 5 squared times 4 divided. I get 8.1487. I'm just carrying a lot out because I may need that in the future. If this was actually my answer, I would round it. Okay. Is that what you got? All right. So it has no meaning. It's just a number unless we know what the material is. Once we know what the material is, then we're like, oh, I should go check. So I said it's copper. We think this is compressive, right? It's pushing in both directions, so it's compressing it. So this actually is a compressive stress. So I would put a little C on there. And I'd probably even like note it out here too, that it's compressive. Okay. So in the back of the book, there's a table we should get comfortable with. Start looking at a lot. And it's the average properties, typical average properties of some common materials. And we'll find copper in it. So there's copper hard drawn. There's no other choices. So we'll say that's what it is. And it goes through things like density. So that's how much it weighs per cubic foot, right? Pounds per cubic foot. It has modulus of elasticity, which we're going to talk about today. It has modulus of rigidity. We might not talk about that one today. Then it has tensile yield strength, 40. So the yield strength is the strength in which it starts to deform permanently. So it's not failure. It's like you pull on it, you let go of it, it doesn't go back. That's the tensile yield strength, okay? Right before that, you pull on it, you let go of it, it goes back. Everything has an elastic region. The tensile yield strength is the very upper end of that elastic region. Typically an area we don't want to go to, right? We don't want things to bend and then we unload it and it stays permanently bent. That's a bad thing. Just think about a bicycle. You jump it, it gets all bent, like now that bike's no good. It didn't fail other than it bent and deformed permanently. That is a failure, okay? So this is one of our kind of guiding lights that we use. We check this all the time. We don't want to be anywhere near the tensile yield strength, okay? So copper is what? 40 KSI. Now, this is tensile. It doesn't give us a compressive, and that's pretty common, that you're not given a separate compressive yield strength. A lot of times we just use both. Tensile and compressive both work just fine. Ultimate is actually failure, so we don't even want to go here. So they give this to us because when we get into design, there is something called an ultimate design. So if we're using ultimate design, we will use this number and then we'll bring it down by a factor of safety. So when we get to designing stuff, like there's a whole section in there, we'll talk more about like common ways of designing and then this ultimate way of designing, which can make things a little more economical, a little cheaper that way. All right, so 40, right? And we got what? We got 8, yeah. So it's good, right? So that means if this thing is made out of copper, this carries that no problem. Like it's gonna stretch or compress when you do this, but when you take the load off, it's gonna come back into shape and it can do it no problem. That's it. That's like the kind of the sweet spot of this class allows us to do this kind of analysis. Like, hey, that works. And it's got a factor of safety. Factor of safety is about what? 840, approximately 5, a little under 5 probably. It's a pretty good factor of safety. All right, let's do the 2x2. Black. So, you know, I don't know, segment 1 maybe. And then this side is also in compression, right? Because it has 22 coming in and it has 22 coming in. So the 10 and the 12, all of that have to transmit through this piece. So this is also a compressive. It's of the second segment. We're going to use P over A. Our load is 22K. And then what's our area? 4 inches squared. 2 inches by 2 inches. .5 KSI compressive. Same material, they didn't change the material. We already know that the yield is 40 for a hard copper. It went down, does that make sense? Sure. So it looks like it's a bigger cross section. The bigger the cross section, the more area you have, the larger the denominator, it drives the number down. So if you're in a situation where things are right at the limit, you need to drive the area up. If you can't change the load, you got to drive the area up. Yeah. Why do we use 22 instead of 10, 12, 22? Yeah, so if I section it here, got 22 coming in. I got to have 22 coming in. 12 and 10, 12 and 10. It all transmits through, right? Yeah. So here, yeah. So what's it feel right here? It feels 10 coming in, and then it feels 12 going away and 22 coming in. it transmits all the way through the member. It has to carry. So it can change, like when you have intermediate loads like that, a bearing, some kind of plate where something's mounted to it, it'll change as you go through the system. So I just was looking at next to me where I live, they're building a new house and they dropped trusses yesterday. So I walked over and I was looking at the trusses. And one of the trusses comes down with a 2x6 and then stops and then plates up to a 2x4. Actually, it's up here, plates up to a 2x4. So this is 2x4, this is 2x6. So interesting. I've not seen one like that before. It did have, you know, structures coming off it, but this load coming down here, traveling through, you know, comes through 2x6, goes through 2x4. That load's still got to get down there. It doesn't get to come here and just stop. Whatever snow load's coming has to travel down. So the load here, bigger area, load here, smaller area.
Well, then if it's all feeling like all those pressures, like all those forces, right? Why aren't we just adding up all the forces?
Because they're different directions. If they were all going the same way, you would. Right? One goes to the right, one goes to the right, one goes to the left.
It's just weird that you say like all the forces go through it, but then we're only taking like one number.
Yeah, so I didn't, like, I could have put a force in here going some other direction than this force, but that wouldn't make sense with the truss. But with the machine system, this is probably some kind of machine system, we get forces going in all directions. So, Brian, do this, section it, right? Draw that section and say, okay, 10K in, right? What do these fibers got to feel for this thing to be in equilibrium? It's got to feel 10K in. If I look at the other side, so here's the section again, and now I'm going to look at this side. I got 22, I got 12, because I didn't do anything to this. This is all working as one piece. What puts it in balance? 10K. Now it flips direction, but it's still compressive, and that's all we care about. Does that somewhat help? So wait, this is where you got to shift from like external forces to like, what are the fibers inside feeling? And they feel differently here and here, like they feel different stuff. Okay. All right, so we got our two stresses. We compared it to material. I think that's all they wanted, right? In this problem? Yeah, just stress in A and stress in B. So we'll come back to this, but other things we can calculate is what's its change in size? Like, hey, okay, you got 10K, that's not a small number, that's 10,000 pounds on a piece of copper this big. It's got to change some shape. And copper is actually fairly ductile, right? It changes shape pretty well. So how much shape does it change? That's important, especially if there's some kind of clearance going on inside here that's tight. And most machine systems have a very tight tolerance inside there. You can think of a motor and piston rods, and you know, we can throw in some temperature, which we'll do in this class. You can get some change in shape big time. So you have to accommodate for that, or else cylinder walls, you know, pistons expand into cylinder walls and create unusual amount of friction and weld together, and it's done, right? So that can happen for a lot of different reasons, but at normal operating temperatures and torques, those kind of tolerances are counted, right? It's when the temperatures go crazy that you have more expansion than you have clearance and you get problems. So we can calculate this kind of deformation. The next kind of piece, I'll do that one and then I'll come back to shear stress, is epsilon, which is strain. So strain is how much something changes in shape. So we have the copper, we have the load. We know it's going to change in shape, but we don't know how much it's going to change. So the strain equation is the change over L. So delta means the actual change. L means the original length. So we had this kind of setup. And I think I said, what kind of lengths did I say? Yeah, 10 inches and 15 inches. And then we had 8.147. So we have a stress in this one of 8.1471487 KSI, and we had 5.5 KSI. So we know something about the stress, we know the length, we don't know how much it changed, and we don't know the strain value, okay? So this, you can calculate strain if you know the change and you know the original length. Well, we know the original length, but we don't know how much it changed, right? So we have to go after this kind of information kind of in a little different way. We have to use another material property. So I'm going to talk a lot about material properties. Yield stress, that's material property. When we got copper equal to a yield stress of 40 KSI, that's a material property. Right? If I looked up steel, it's going to be different than copper. If I look up concrete, it's going to be different than copper. It's based on the material. Okay. The other material property you can look up is called E. Young's, named after the gentleman who discovered it. Modulus, Young's modulus. It's also called the modulus of elasticity if you want to get rid of Young's name out of there. But you'll see both, modulus elasticity and Young's modulus. And this is also a material property, which means you can look it up for the material. Okay. So here's the catch. E, Young's modulus, is equal to stress, which we know what stress is kind of now, over strain. There's a relationship between the load you put on something and how much it deforms. Does that make sense? Like, take a rubber band, if you put 1 pound on it, it's like this. Put 2 pounds on it, it's like this. There's a relationship between stretch and load. That's what Young's modulus is. Okay? So to figure out how much something deformed, you got to know the property. It's copper. You got to be able to look this up and put it here, right? And then you got to be able to calculate the stress. Well, we calculated stress. We got those. We should be able to look this up. Then we could find strain. Once you have strain, you put it here and you know the length, then you can get delta. So it's almost always a couple step process. Okay. This is the change. Yeah, so delta is usually very small. And this is the original length. So in math, delta, I think, is a triangle. And it also stands for how much something changes. So just know that we are using the same thing and just have a different symbol for it. The book doesn't. I'll know what you're talking about. So yeah, that's fine. Okay, so let's just, I want to work it. I know I'm throwing a lot out, but that's okay. I want to work it through and find out, hey, how much did this change in size? I want to know. So we got to look E up and look at its units. It's on that same properties page in the back of the book here. Focus. And what's E? Modulus elasticity. E, it's in KSI. 15,000 KSI. Yeah, so that's an easy one to kind of mess up. Modulus elasticity is a huge number. 15,000 KSI. Again, that's a material property. And they get it from test specimens. So they pull on pieces and say, oh, it's stretching this much under this load. And they do that for the elastic range, which I'll talk about the elastic range in a second. And then determine Young's modulus, and they'll send it to you if you're not taking it out of a book. So when I order structural steel, I ask for the data for that steel. They send you this, and they'll send you Young's modulus or modulus elasticity for that steel run. So it's not something you would look up. It would come with your purchase if you're going to do something structural with it. Yeah. Yeah, it's each run. So if I'm buying small quantities, they have it for that run. So, yep. Like if I was buying an A36, which is 36,000 yield, or 36,000 or 30,000 KSI for the modulus, it might be 30,000 plus or minus 100. Yeah, it's pretty small. And remember, we're not anywhere near kind of the yield, so we have factors of safety. But it's nice to know the real number. It's pretty close to a published number. All right, so we know this. Let's do this larger one right here. Segment 1, maybe they called it. Here, I'll call it 1. Segment 1. Okay, so we know now 15,000 KSI for the modulus elasticity. We know the stress because we calculated 8.1487 KSI, and we want to find the strain. So you would want the strain if you want to know how much something changes in size, because strain is all about the relationship between original and change. Okay, so we do want the strain. So we calculate that. So it's going to be the 8.1487 divided by 15,000. So pretty small number, right? Should be 0.00054325. What are the units of that? Yeah, they're nothing. And actually, right, it's KSI over KSI, but we refer to strain as inches per inch or millimeter per millimeter, which is weird. I get that, but what it is how much it changes per inch. So in this case, it changes 0.00054325 inches for every inch. Isn't that weird? Yeah. Hard copper, pretty resilient, huh? In every inch, yeah, that's the key though. So we refer to it as inches per inch. So it's how many inches it changes in every inch, right? So it's not much per every 1 inch. So then how much does our segment change? Well, it changes that much per inch. I have 10 inches, so 10 times the value. That's how much it changes. So this equation does that for me, but logic also does it for you, right? If it's this many inches per inch and it's 10 inches long, then just multiply the 10. And it tells you to do that. To get delta, whoops, sorry. To get delta, we would take L times epsilon, right? This is the strain, so we just multiply by L. But if you understand what this is in concept, then that it's a no-brainer to get to total deformation. This is per unit deformation. We multiply by 10 and we get delta, which is, just move it over, right? 0.0054325. Now it's just inches. So that's how much that segment changes. Not very much, which that might be a good thing. Because if the temperature rises, it's going to change some more. Or if the temperature cools, it'll change some more. So we'll kind of calculate these elongations and add them and subtract them. Figure out what's happening in total.
Yeah, right there at the end of that number, right? Down right there.
Inches per inch?
Oh, inches per inch.
Yep. And I put a 1 there. Because it is inches per 1 inch. So then we could calculate the change in the 2x2. There's less stress on it, right? 5.5. It's longer. So we have to go through the same thing. We use our modulus elasticity because it's the same material. If it was a different material, we'd look it up. So for segment 2, we're going to take our 15,000 KSI, set it equal to the stress, 5.5 KSI, and calculate a new strain, right? Because it's a different area. So we take the 5.5, divide by 15,000. We get a small number for epsilon. 0.0036667 inches per inch, because that's how our strain works. And then how many inches do we have on this one? 15 times. So this one's actually changing 5.5 thousandths, right? Because I multiplied 10 times 15 inches. So, you know, that's not negligible. That's a pretty big change if you had a tight system with tight clearances. So if you're like plus or minus, 2 thousandths on this end, and that's all the clearance you got, and we're moving 5, that's a problem. Yield. Yeah, so that's a stress, the tensile yield stress. They call it strength. I don't know why, but it's a stress in KSI. So just focusing on the word yield, that means it yields. And when something yields, it doesn't return. And we want to stay within the elastic range. We want it to stretch, let go of it, comes back to shape, right? When the bridge, like if you ever get stuck on one of the big bridges downtown, like if you're stuck and then the lower deck is still going, your car just sits there and bounces. Well, that's all of the members expanding and contracting as vehicles, trucks, usually big trucks, go across. They stretch, they get past it, they come back into shape. So all that's going on as we're crossing bridges or any loaded condition like that. Even when we don't feel it, like you could calculate my body weight on this concrete and calculate the deformation. It would be so damn small, but there would be a number there that you could calculate because there's really nothing that doesn't compress. There's definitely materials that don't want to compress, but they all have modulus elasticity. So if it's got the modulus of elasticity, then it has to be able to stretch at some point. Okay, so we should talk about that because that's a super important part. because these numbers, calculating these numbers, they're only valid. In other words, we can only use them if we are within this modulus of elasticity range, and that's the elastic range of a material, okay? If it's outside the elastic range or over the yield stress, we can't do it. It's in permanent deformation. We can't calculate deformation because it deformed and is not coming back. It's just outside of the predictable range, okay? So I'll show you the most classic graph of a material so you kind of understand this, and that's mild steel. Mild steel creates the best graph. And I'm going to draw it. It's in the book, but makes more sense if I draw it because we can talk our way through it. So it is a graph, and the way it works, and I'll put up a video, or you can search tensile test, and you'll see how it's done. We have a tensile test machine, and we will stretch some material till it breaks. It's pretty fun. But what happens is they take they call them specimens of material, whatever material you want the material properties of. So if this is mild steel, looks something like this, and then they grab it here and they pull, and they grab it here and they pull, right? And they have a strain gauge on here. So they understand the deformation. So if you pull on it 1 pound, the strain gauge moves. And this is usually like 1/2 inch. So it's, you know, it's like your little finger size. So even 1 pound, the strain gauge is going to sense that. Then obviously, if you let go at the pound, it goes right back to shape. No problem. So across, I want to make my graph wrong. I want to make it just like theirs. Did they put a deformation across the bottom? Oh, maybe they didn't do it. Yeah, so this is strain, and this is stress. All right, so we've talked about it a little bit. We haven't done a lot with it. What was stress equal to? P over A. So this essentially is the load. The A doesn't change. The area of my specimen is going to be the same throughout. But essentially, this is load going up. We use stress because we're going to divide by A and get the stress, right? And then strain, we know what that is. That's the change over L. So strain is deformation, right? So as we put load on it, deformation goes up. That makes sense? All right, so the classic graph created by mild steel, and this is why we like mild steel so much, starts linear. In other words, if I put load on it, I get strain. If I put more load on it, I get an equivalent, consistent strain. More load on it, more strain. More load, more strain. I get a nice stretch region, okay? At some point, this curls over. In other words, I have so much load that now the strain is starting to change at a different rate than it did here. This is linear, consistent, right? And then it changes. This is the yield. That's where we have permanent yield. Notice what happens to the load. Comes down. So you get to a certain spot and you stop putting load on it and you just watch it and you just watch the load come down. And that means you're past the yield point. It is yielding under the same load. It continues to stretch. We're down here, put a load on it, it stretches, it stops. It's happy with that. But at some point, you're going to just like overdo it. And you can do this with, you know, plastic material, like a lunch bag. Take it and pull on a little, let go, it's the lunch bag. But if you pull on a lot, then it's like all stretched out, right? Well, that's load. You can continue pulling with the same amount and just keep stretching, right? That's what's happening here.
So the yield itself is the point where it's going to start.
It's actually a little past it. They give us a little bit. So we get, it's called 2%. We get, if you let go of it right here, it returns to there with a little bit of permanent deformation, but acceptable. And this is kind of exploded. It's really tiny, like you wouldn't even see it. Yeah. So this region, the linear region, that is E, modulus of elasticity, where the stress and the strain and the stress and the strain and the stress and the strain are all equal ratio. This is where we work. Never going outside of it. I'm going to draw this region in red, and it is the elastic. Make sense? Like the rubber band region of steel. You put a load on, let go, it goes boom, right back to the same shape it was. Well, that's cool. Almost all materials do that. So mild steel is not unique. It has a good elastic range, but it's not as good as, you know, more elastic like rubber. Rubber's got a fantastic one. It'll elongate crazy. Let go of it, comes right back to it, right? Doesn't do great carrying a load, but it's got great elasticity. Fantastic. The thing we like about mild steel and other steels, why they are so popular, first, they're fairly cheap to make. That's a good thing. They have a second life. Yeah. So what happens is it yields, it dips, and then it's called strain hardens. It gets stronger. It's phenomenal. And it's fantastic because if we design in this region and then the earthquake quakes above what we planned, it shakes it, it permanently deforms it, but then it gets stronger. So it's still going to be like all tweaked out, but it doesn't fail until here. That's where it fails. This is full fracture. This is breaks. So if we've designed well in the elastic region, we never get near this. And we have this as a safety backup, the strain hardening. Okay. So that's why we like mild steel so much. This is where we work in Young's modulus, in the region where stress and strain are consistent and predictable. This is predictable. This is not predictable. No, well, not in the US, absolutely not. Yeah, not in our code system. Yep. And actually, we very seldom go right to there. I would only design to here if there was no life threat whatsoever in whatever I was designing. So maybe if I was designing a triangle, right? And I was like, oh, you know, it could kill me somehow, I'm sure, but it's not life threatening, right? If there's no threat of life or safety, then you can sometimes get right up to it. No reason not to. But like if you think about most things that come in contact with humans, there's a possibility it could hurt somebody. Then there's factors of safety off of this. So let's think about that. A factor of safety of 2, put your design limit right there. And 2's nothing. Like we put 2 on everything. So that's good. That lets us drive across any bridge we want to drive across and not even think about it. So unless it's a 200-year-old bridge, which we have some of those hanging out still. So that's a different problem. Good. Elastic region. Yeah. So what happens when they pull on this? And if you do, I'll post up some links so you can look at it. But they have, you know, nice slow-mo footage of it going with a graph next to it. That's when it's kind of cool. And through this region, you'll see no change. And you can actually see the diameter kind of get smaller because it's stretching. That material's got to go somewhere. The diameter gets smaller, which is not helping us. As we know, as the area gets smaller, the stresses go up. But then right at the very top, it curls over, the load stops, and then we have what's called fish scaling. That's the first thing you'll see. So that's the other thing that mild steel does really well is gives you lots of warning. Like it'll fish scale and then it strain hardens, which it becomes a different material and you can actually see the surface area change. So on the molecular level, it's a different material than what you started with. So it's strain hardening. It's way more brittle. It is way stronger, but stronger is not necessarily great for bending. So if there's any bending load, it's become brittle and it'll break. So it's super cool. Then you'll see necking. Necking occurs where there's the highest population of carbon pockets. In steel, we get carbon, right? And we don't want any carbon pockets in steel. So they actually test it by cutting it every now and then and making sure it's as pure as they need it. But there's something in there, right? Some kind of imperfection in those little molecules. Wherever that weakest spot is, it actually necks down and then it fails. But that's not predictable. It could, it can be down here, it can be anywhere. So yeah, it's pretty fascinating. And then of course this graph is made over and over and over, and then they average it, and then they give us a table in the book that we can go by. And that works for all materials. Titanium, we're all kind of aware of titanium. It's super strong. You know anything else about titanium? Huh? It's super light. High melting point. What about, how's it doing bending? Super brittle. So here's titanium. Like if I use the same relationship in the graph, titanium would look something like that. And there's the failure. Which is the problem? There's no warning whatsoever. There's no deformation. It's super stiff. But when it goes, it's a massive explosion. So when we first made titanium bicycles, the failure of the bicycle was so violent that shrapnel would come off of the failure and into the legs of cyclists. It was brutal and just like razor sharp when it fails. So, huh? Yeah, I don't know. My guess on lead would be like that. I don't think it has any elastic. Like, I think if you take lead and pull it, it stays there, even under really small loads, but you could probably look it up. Some of these are hard to find if they're not like a structural material we use. Like engineers aren't gonna be like testing this stuff. Like aluminum you can find. Aluminum is actually pretty good. It's in between. It's not as strong, but it has a longer elasticity range. So it does pretty well in elasticity. It just bends fairly easy. Super light though. So that's where we get like material properties. That's what the next chapter is. And it's just a massive read. So I usually just skip it and talk about material properties through the term because it's not going to do you a lot of good to read chapter 10. It's just too much. But it is interesting, all the different properties there are. Like, you'll go through it. But it takes all the properties to make a good material for whatever you're working on, right? You can't just look at modulus elasticity and say, oh, this is the right one. Well, if it's mild steel, it's going to corrode like crazy. We're not going to use it in a boat on the ocean, right? It's going to be gone in a year if you do that. So you have to think about, oh, geez, I'd love to use, hard copper for this airplane part, but it's heavy as heck. And we need to lighten every part in an aircraft just to get it off the ground, right? So weight becomes a thing in aircraft. Trains, not so much. Like, I swear, they try to make them as heavy as possible. Just once they get them going, you just like turn the engine off and it goes for 500 miles just out of inertia. So, different applications are going to use different materials based on everything. And you can never like say from one thing, this thing is strong enough. You just can't do it. You have to look at everything. So, all right. I think that's good. You're going to do, I think you might have a 10, 15, and 18. Let's look at that though. 10, 15, 18 out of chapter 9. Either way, I'm taking them either way. So the last two homeworks, I got some in person and some submitted. So. Let's see if I threw in a shear stress one. Because I didn't talk about shear stress. Yeah, 10 is shear stress. So let me just explain shear stress super fast because notice it's the same equation. Shear And then compressive and tensile are here, P over A, P over A. So if we take this rod and we pull on it, what kind of stress is that? Tensile stress, right? So this is tensile stress, and we would use this 30 kips and this area to calculate it, okay? Shear stress, tensile stress, the load is perpendicular to the area. Does that make sense? Like if I take the pin and I pull on it out this way, it's perpendicular to that round area, correct? Shear stress is parallel to the area. So the only way I could get shear stress here would be as if I put this thing on some kind of big block and then took another block and went down. And then this went up. I'm now putting my load in line with the area, shear stress. Now, if it was the same amount, 30 kips, it's going to be the same stress. So it's still just P over A, but your load is in line with the area you're thinking about. So here's probably the best example. I take two plates. Testing my ability to, and I pull on them, and this area right here, I glue. Do you see that? Two plates, I glue it together. You know, whatever, Gorilla Glue, some kind of fancy glue, right? And then I pull on it with my 30 kips. There's a couple different stresses I could calculate. I could calculate the tensile stress in this piece, which would be using this cross-sectional area. That's what we've been doing, right? I could calculate that tensile stress, but I could also calculate the shear stress of the glue because that area is in line with or parallel to the load. So that's a shear stress. That's a tensile stress. That makes sense? When you think about a shear in a machine shop or a fabrication thing, that's something that just cuts cuts material off. That's what a shear does. Scissors, shear material, right? If I have a stick and I take my kitchen scissors or flowers and I cut that stem off, I'm shearing it, going right through, okay? So when the load is parallel to, it is shear stress. When the load is perpendicular to, it is tensile stress. All right, that's definitely good enough for your homework on that. They get weird because like if you're to punch a hole, like a hole punch through something, that's a shear because the load is in line with what's failing, but what's failing looks like a wedding ring. It's that area. So you have to think about like, what is the area that's failing, right? A clevis and a pin. Like that. And if I put a pin through and then I put this piece on, right? And I go like this and this, or a bolt or whatever, what has to fail? If the bolt fails, what has to fail? Well, that area and that area. Two areas have to fail. That's why we like these, because it doubles my shear, right? And if I actually did it like a piano hinge, then now you have multiple areas that you have to think about what has to fail. Like not just one of them would fail, they'd both have to fail. So this would be like an area times 2 in this shear problem. So it does get more complicated than this, but this is probably the best example of shear stress. All right, we're done. I can just keep going. I'm going to do a little video on chapter 10. I think chapter 10, is that material properties? Yeah, I'll do a little video on chapter 10 and you can watch that. Yep, that's correct.